To have Jordi Miralda Escudé as our speaker today over Zoom for today's DTP colloquium. Jordi did his PhD from Princeton in 1991, and then he was a postdoc at Cambridge University in England, and then at the Institute for Advanced Studies in Princeton. And then since 1996, he has been a faculty member at University of Pennsylvania, the Ohio State University, and then the Autonomous University of Barcelona and the University of Barcelona in Catalonia. He's currently a professor at the University of Barcelona at the Institute of Cosmology there. So more importantly, probably Jordi has made very significant and important pioneering contributions to the fields of reionization and intergalactic medium studies in cosmology. His main areas of interest are the intergalactic medium and gravitational lensing. He has also produced really important results in the Lyman alpha forest, for example. So I would like to especially thank Jordi for agreeing to talk to us over Zoom today. After his talk is over, Jordi has agreed to hang around in the Zoom meeting room for discussions with students and postdocs. But otherwise, Jordi, we can start whenever you want.
Thank you very much. I appreciate Girish, and thank you also for your invitation. I'm very glad to give you this colloquium, and I'm just sorry that I couldn't travel to India this time. But you know, I hope I can still come at some point in the future. And so the seminar, as you see, is about gravitational lensing, but specifically about cases where we have very, very high magnification. And where we can actually see a star which is not a supernova, but you know, normal star at cosmological distances, and how this can be a probe to the nature of dark matter. So I would like to mention my collaborators, Liang Dai, Teja Venumadhav, Sasha Kaurov, especially. So the work I will be describing to you is thanks to them, basically. So you know, I really have had a wonderful time working with them. So just to start, I will mention this gravitational lensing in clusters of galaxies. That's what I'll be talking about. And this was the first galaxy cluster where strong lensing was discovered, not of a quasar, but a galaxy that is lensed, and you resolve the image and you see these typical images like this arc. This arc in Abell 370, this particular one is called, I think, the Dragonfly lens. The cluster is at redshift 0.37, and there is a galaxy at redshift 0.72, which is being lensed. And this is typical of many such things. So in a galaxy, in a cluster, you have a substructure. There's two most massive galaxies in this cluster near the center. And there is basically a dark matter halo. So, you know, the lensing shows that indeed it confirms the presence of dark matter with a lot more mass than the visible baryonic mass. And here in the right, you can see this wonderful, you know, zoom in of this arc with the Hubble Space Telescope, so we can get very high resolution, and it's really fantastic opportunity here to study the lensing in detail. So you see that here there is this spiral galaxy in the background that's star forming at redshift 0.72, and this part of the galaxy here has gone into the region of very high magnification. So all this yellow thing here that's so elongated is basically this bulge, the central part of the galaxy, re-imaged over here. And there's many of these blue blobs in the disk that have several images along this thing. So you can basically follow this, that this is the other edge of the galaxy, and you know, map the way that light has been deflected by the overall mass distribution. There's a nice review of all these in this Umetsu 2020. The nice thing is that lensing is directly sensitive to all the mass. So here is, in a way, the only place where we are observing all the mass directly, and most of which is dark matter. There's no other such neat way, direct way of measuring the dark matter in the universe. And so this, what we can say is that generally the observations we have had in clusters of galaxies on gravitational lensing agree with these predictions of the cold dark matter theory on such things as the mean density profiles of clusters, the fact that they should not be spherical. There's some ellipticity distribution, and the dark matter also has some, generically triaxial distribution, the presence of substructure, and so on and so forth. But so what would be nice also is to be able to probe the small scale distribution of the dark matter. So in particular, is the dark matter just kind of smoothly distributed, diffuse matter forming these halos around galaxies and clusters, or is there some small scale structure? And this, if we could answer this question, it would go some way towards probing the nature of the dark matter. It would be very interesting to know, this basic question in cosmology: what is the dark matter? So, just to mention a few things about how lensing works. I suppose you've seen very often this typical lensing diagram. We are here, the observer. The source is here. This is the lensing deflector. If the lens wasn't there, light would travel along this direct line to us. But because the lens is there, then what we actually see is the light ray that was emitted here and then was deflected by this angle alpha, right? And then when we study the direction on which we see the image of a source as a function of the source position here, we get a mapping. Okay, so we can define here source plane. There's a position that is two-dimensional because it's the two angles of the position on the sky of the source. But then as a function of the lens position or the image plane position, we get, if we follow the light ray back, we get mapped into another position of the source plane. Okay, so then the important thing in lensing that determines when you have very high magnification is what's called caustic lines and critical lines. And in general, the way we define this is, well, in this plot, I've done an example of a very simple lens model, which is just a pure ellipticity. So you take a lens model that has a density profile with a core, but then it is just elliptical. Instead of being a spherical lens, then it is just an ellipticity and nothing else. So this is very simple. So then you have, first of all, critical lines, which are the dashed lines here. And in this case, there are two. Okay, and critical lines are in the image plane. And in this case, I have superposed in the same plot the source plane as well as the image plane. And in the source plane, you have caustics, which are the dotted lines here. And then at every point in the image plane, I can ask, what is the magnification matrix? So that means magnification matrix is this A. That means looking at how the source position Y varies as I move the image plane position X. These are two-dimensional vectors. So then when I do this derivative, I get this 2x2 matrix. Okay, this is the magnification matrix. How the source position that I go to, if I follow backwards, the light ray varies with the image position. So I define these, these values of the magnification matrix here, and where this magnification matrix has zero determinant, so it has some kind of a degeneracy, then I get these critical lines on the image plane, right? And so whenever this is not like actually inverse magnification. So whenever I can diagonalize this matrix and one of the two eigenvalues is zero, then I get this this catastrophe, and this means that the magnification is the inverse of this determinant, so it will go to infinity. Okay, and then the mapping of these critical lines onto the source plane gives me these caustics. So this is the typical thing I have. This critical line, which is this outer one where images get tangentially magnified, goes into this characteristic asteroid caustic near the center. Okay, and then this is one is associated with the core. It has radial magnification. Okay, so now if you imagine that there is the source, I've drawn the source, possible source as a little circle here, then in this case, the source produces 5 images. First one that's highly demagnified near the center, and then 1, 2, 3, and 4 that are magnified. And these 3 and 4 in this case are near the critical line. Okay, so they're near the critical line at this point that corresponds to this point in the caustic. So the part that is inside the caustic gets 2 additional images, and the part of the galaxy that's outside the caustic is not imaged here. Okay, and then when you get near the critical line, here is where the magnification goes highest. So the part of the galaxy that just touching the caustic here will produce images that are very, very highly magnified near the critical line. And this is what we see, and this is kind of like that arc we were seeing before. So this is basically a summary of how strong gravitational lensing works. And then in theory, if you just take this idealized theory here, the magnification is infinity, as I said, for a source that is, if you have a point source that's exactly on the caustic, and then you get two images that are kind of merging here in the critical line. But what is the limit in practice to what's the maximum magnification you could possibly achieve on a source? There is three such limits. First of all, the angular size of the source. Of course, if the source is not really a point of light, then you have to average the magnification over some size, and then you get finite magnification. So of course, to start with, you never have really any source that is perfectly point-like, right? So that will give you one limit to the magnification, but then there's also another two. The second one is diffraction, right? So if you go to the limit where wavelength of the light matters, it gets diffracted, then this will also provide a limitation to magnification. Now in this talk, diffraction is not going to be important, so I can use geometric optics whenever I have, you know, in the case of highly magnified stars, which I'm going to be interested in the optical, diffraction you can calculate it, and it's not important in limiting the maximum magnification. But there is a third phenomenon, which is microlensing in the cluster, causing what I call corrugation of the caustics. And this means that in this cluster, you can imagine that this is a cluster with lots of galaxies here, approximately elliptical. But then when I go to look at this image close to the critical line, there may be a lot of stars here in the cluster, right? And stars may look like, you know, they're negligible. The mass of a star is so small compared to the cluster of galaxies. But when you get near the critical line, then the presence of stars here means that you will get microlensing. And then the microlensing means that instead of having a smooth caustic, you'll have a corrugation of many, many small microcaustics. So then this caustic looks a lot more complicated on small scales. And this will also reduce the maximum magnification that is attainable. Okay, so lensing near a caustic, this is what we'll be interested in if we want to understand how you can get the maximum magnification that we're likely to observe. And then the inverse magnification matrix is this thing, as I mentioned. So when I get close to, let's imagine that this is now the caustic, a small part of the caustic I was showing before, and I have the source, and the source getting closer and closer to the caustic. And then what happens as I get close? Well, in the corresponding image plane, I have this critical curve, which is the part corresponding to this caustic curve. And then this source, when it's in the right side, inside the caustic, will generate these two images, very highly elongated, right? This is basically the magnification. And then the magnification of those images will be just proportional to the distance from the critical line. Okay, so I have put a D here, which is the gradient of the eigenvalue that is 0 on the critical line. And then basically magnification, inverse of magnification, is just proportional to the separation X in the image plane from the critical line. And when I go to the image plane, then the total magnification of the two images turns out to be proportional to the inverse square root of the separation of the source from the caustic. Okay, I just have to do the mapping, and then you find that this kappa naught is the convergence at the position of the caustic. It comes from the other eigenvalue of the two. Okay, so that's basically the way I expect magnification to behave close to a lensing caustic. And so the idea now is that if we think about one of those galaxies, like the first one we were looking at here, you know, near a caustic, the galaxy has produced this very long arc you see here. So then when I look at the place where the caustic is just crossing the source galaxy, now imagine that this galaxy you see here, which is a nearby galaxy, any nearby galaxy with star formation, this one is NGC 1559. Okay, so is behind a cluster, and now I have the lensing critical line, and in the source plane, the lensing caustic, and this caustic is sweeping by these galaxies, moving across it. Why is it moving across it? Well, because there's angular motions, right? The galaxy is moving, the cluster of galaxies in front of it is moving with some other random velocity. And this random velocity is going to be due to all the large-scale structure of the universe, right? The cluster is being attracted towards some place on a large scale, the galaxy behind also, you know, the local group, we are in the Milky Way, the local group, we are also being pulled towards the beautiful cluster, we have our own peculiar velocity. So all of this adds up to some overall motion as viewed by us of this caustic of the cluster projected on the source plane, sweeping by this source, okay? And as the caustic sweeps by, then any stars, and in fact any H2 regions or anything in this galaxy, at some point will just get crossed over by the caustic, and then is when we will get the highest magnification, okay? So this is the magnification, as I said, in terms of the position on the source, the delta Y separation from the caustic. And then if I put this in terms of time that I'm observing, well, the delta Y is just the effective transverse velocity that results from the combination of all these velocities times the time minus T naught, where T naught is the time when the caustic is crossing over the source. And then I put this angular diameter distance to the source here to go from a physical separation to an angular one. Okay. So then when I put typical numbers into this, you know, magnification as a function of time, I get this quantity. And then I have put here numbers that are, so if I imagine a star, then I put, you know, typical transverse velocity I will get from large scale structure, about 1,000 kilometers per second, cosmological distance for this distance to the source plane, a time of 1 hour here. Okay, so you see that you can get magnifications of several million over timescales of 1 hour. And this, of course, the maximum magnification you will get will depend on the size of the star. Okay, so basically for a star of a few solar radii, then it takes about 1 hour to cross over the radius of the star at this typical speed of 1,000 kilometers per second. So that's basically the maximum magnification you would get if everything would work in this idealized way. You know, just the caustic of the cluster sweeping over the size, the star and its radius, right? And I'm ignoring here that microlensing that is going to be the thing that is going to limit the maximum magnification. So if everything was in the idealized case of smooth mass distribution with no microlensing, you would get up to this about 1 million times magnified. Okay, so then that's the light curve I would expect. In this case, you know, magnification as a function of time. And now I'm imagining that the star is outside the caustic first, then the caustic moves, right? And then the star gets inside the caustic. So then what happens is that as time goes on, there are 2 images of the star appearing in the caustic and in the critical line. So when I go back to the image plane, then in the critical line, suddenly I have 2 images of the star appearing, and first they are merged and then they separate and then they move out, right? And of course it can happen the other way around too. It'll be 50% of the time each way. But so then the light curve I expect, as I said before, for a point source, it goes as 1 over the square root of the separation or the time. And then you can calculate what it will be for any physical star. So for example, if you imagine the star being a disk of light, but of uniform brightness, then you get this light curve that is the solid line here, right? This is how the flux of the magnified star would vary, adding up the 2 images, right? Imagining that you don't resolve, of course, the 2 images which are very, very close, okay? But so this is the light curve you would expect. And you can calculate this for, you know, if you want to have limb darkening in the disk of the star and given band, you can also calculate it in more detail. But it's something predictable, okay? So basically, this is what you would get. And then the question is, could this be observed? Well, if you ask, what's the maximum magnification that you can get? It's this 4 million, and then here I put in terms of the radius of the star. So, you know, you start with a rather luminous star, because if you have a star like the sun, well, even with very high magnification, it's going to be hard to see it at something like redshift 1 or even redshift 0.72, like that galaxy I showed first. Okay, so you probably need a luminous star so that you can actually be able to see it with something like the Hubble Space Telescope at present, maybe the best telescope to see a very faint source, or maybe you know, one of the very large ground-based telescopes. Okay, so with magnification of 1 million, if you calculate what star you would be able to see at the cosmological distance, if we start with a magnification of 1 million, then let's assume that you're at redshift 1 and you can reach magnitude 28 by integrating in a reasonable amount of time with, say, Hubble Space Telescope. If you can see the image at magnitude 28, then you can go down to a star of 500 solar luminosities, and with magnification of 1 million, you'd be able to see it at this magnitude. Okay. Now the problem is, of course, this lasts for a short time. Okay, so this magnification would be reached for such a star with typical radius 10 solar radii. You know, it would only be about a day when the star is sufficiently close to the caustic that it gets this magnitude, and then it moves out and it gets fainter, right? The rate of crossings, however, is only about 1 per 30 years when you calculate a reasonable stellar population. So how many stars, 500 solar luminosities, do you have in such a galaxy? And then you know, you just, all of them would get swept by the caustic, right? But then you have so many stars, so it would take maybe a few 100 million years for the caustic to sweep over the whole galaxy, and during this time you get maybe 1 event per 30 years. So then when you look at this, it looks rather difficult, right? In a typical galaxy crossed at this velocity, only 1 event every 30 years, but then it lasts only for a day and magnitude 28, that's rather difficult to see. But then you have also the more luminous stars. So then you will have stars of, say, 50,000 solar luminosities. Okay, these are much more rare. But now, so that means they'll cross, instead of 1 every 30 years, only 1 every 10,000 years. But now it's visible for much longer, okay? Because magnification goes as this one of the square roots. Now it's visible for, you know, it goes like the square of the luminosity. So it's going to be visible for 10,000 times longer. It's going to be visible for about 100 years. So that's 1% of the time. If you look at 100 clusters, you would expect to have one of them where a star of 50,000 luminosities is visible thanks to this magnification, okay? Now, of course, the problem is, if it lasts for 100 years, typically this 28 magnitude image will be almost constant. So how do you tell it's lensed? How do you tell it's a lensed star, right? If it does not vary. Well, here is where microlensing, instead of being a problem, it can actually help us. Because what microlensing will do is that it will reduce the maximum magnification achievable. You will never get to magnification of 1 million, like in this idealized smooth case. It will be less. But when you have a very luminous star, right, with less magnification, you know, it will be close to the caustic for a long time. So then, in addition, you know, during this long time, the magnification will vary, right? Will vary over a much shorter time scale than 100 years, because it's repeatedly crossing microcaustics in this corrugated cluster caustic by the presence of several microlenses. Okay, so that's basically the story, and then it turns out that this. Yes.
Question.
Yes, please.
So this more massive star is also bigger in size.
Yes.
Does that affect the magnification? Will it reduce?
Yes, the magnification is also reduced a bit, because the maximum, you know, the radius, let's say, is instead of 10, maybe 30, 40 solar radius. So then magnification, that's maximum magnification will go as 1 over the square root of the radius.
Okay.
Yeah, so it'll be reduced a little bit, but that's not such a great problem. Actually, the main thing is if you can see variability of these images, and then, you know, you can basically see if it's really a magnified star.
Also,
so then,
instead of the stars, can you also try to look at the globular clusters in the galaxy? Or
yes, if there is a globular cluster just on the caustic, then you may have several events from several stars. But okay, so it turns out that basically to see this, you're really dominated by the most luminous stars, because the hardest thing right now is, you know, this is very faint, so you have to use to discover this Hubble Space Telescope or something that you can see the faintest possible image. And then basically it's always more likely to see something from a most luminous star, because, you know, going to very much higher magnification is very, very rare. So the events you can discover basically are dominated by the most luminous stars in the end. Even though they are more rare, right? It's more likely that you have not such high magnification. So this actually is something that I thought about this possibility back in 1991. Then it was kind of forgotten. I didn't really work more on it. But then when the Hubble Space Telescope started taking deep images of these lensing clusters, it turns out that this is possible to discover with the Hubble Space Telescope, and it was not realized for some time. But fortunately, many images were accumulated during this time. And then in this particular cluster, MAX J1149, so there is a modeling of this cluster in this paper by Zitrin and Broadhurst already from 2009. And in this modeling they did, you know, this white line shows it's the critical line of the cluster that I was talking about, that there's many cluster galaxies here. And in this particular object, there is, you can see 3 images of a background galaxy that are very nice. So 2 images are here near the critical line, and then the 3rd image is here. So it's a very nice case where you have a spiral galaxy, it's magnified, right? The galaxies are redshift 1.49. And then these 2 images are more highly magnified, and there is a part of the galaxy that sits right on the caustic, and it's the outer part of the spiral disk. So then the spiral arms go into the caustic, and here you have very high magnification. Okay. So the thing that was interesting in this cluster is that they discovered a supernova. And this is the same lensing cluster here. This was, you know, the images are here. Yeah, and then they discovered the supernova. So in this particular region near oops, sorry. When they discovered this supernova Refstal. So near this galaxy here, there are these 4 points of light. This is when the supernova went off. Okay, and this supernova had 4 images, and then they got light curves and they compared for the time delays and so on. So then while then HST spent a long time looking at this supernova and getting the time delays. And then while they were observing this, they also had a lot of images of this other part of the cluster. So here is the place where they discovered, they reported in this paper, Kelly et al., that there is this image of a highly magnified star. Okay, and here you can see this region blow up of this thing. So here there are these 2 images, and this one disappeared. This one wasn't here in 2014, it was there in 2016. So there was something that was varying quite a bit. Okay, and this, you know, they basically reported in Kelly et al., and they argued that it's really a highly magnified star. And what's the evidence for this? So this, they call it the transient. Okay, it is just on the predicted position of the critical line of this lens. And essentially, this is a light curve they observed. So they had various observations of the flux from this source. And then the black points here with error bars are the photometry. So they had some observations here, and then they got a lot of observations when the supernova went on. And then you can see the evidence that it's varying, it's something variable, okay? The curves, this kind of simulation curves are only, you know, microlensing statistics. So I have told you about microlensing, and it turns out that all these variations would be produced by microlensing of the stars that are in the cluster, right, together with the dark matter and so on. And you know, they should agree with the points only in a statistical sense, because microlensing is something that's random, right? So there's no reason why they should agree precisely, but in this case they just did the microlensing simulation, which agreed more or less with the peaks they see and this kind of thing, to see that this is typically something that you can understand through microlensing. Okay, but first you have, so we think that this is the first detection of highly magnified star, and this was the work of Kelly et al. And essentially it's because of this variability, because of the colors of this source. And then they took also in this, they did this very nice work where they took photometry in various filters of this object that was varying. And then here you have a kind of spectrum, even though it is photometry, compared to the spectrum you expect from a B star. So then basically this agrees with a star of temperature around 13,000 Kelvin, and this is the Balmer break. So there is evidence for this. So it's evidence that this is essentially a star, supergiant, about blue supergiant, very luminous, one of the most luminous stars in the galaxies, which is consistent with what you would typically get if you just see the first super-magnified event, right? One of these blue supergiants, and essentially this was the evidence they found. Then there is basically, it is varying, but this would be consistent with just the microlensing. Later on, there has been a second discovery here in another cluster. This one is J0416, and it's in this case there is a transient, also something that's varying in one of the positions of this. Again, it's a double image of a galaxy. You can see here that this is the model critical line, and then basically you can see that all the features are reproduced twice, right, consistently around the critical line. So then basically there's something transient observed here, also at the position of the expected critical line in the modeling of this cluster. Okay, so essentially there are these two cases so far, and I think there will be probably more discoveries, and we have these examples of highly magnified stars.
So
okay,
Jordi,
so yes.
Sorry to interrupt you, but why was the microlensing simulated light curve so featureful? Why wasn't it just a flat line in the Kelly object?
These simulations of microlensing, basically, what you have is you put stars on the cluster randomly, right? And then it's the cluster stars that are causing this variation. So if you have just a smooth dark matter, you don't expect any variation, because the time scale for getting close to the caustic or far away from it is very long, maybe hundreds or thousands of years, right? So it will only be this very, very long-term smooth variation. But then when you add the stars, even though the stars are a very small fraction of the surface density compared to the dark matter, they cause this corrugation of the caustics. So now you have a complex structure of microcaustics, and then you're constantly crossing these microcaustics and getting lots of peaks. Mm-hmm. That's what happens. So this microlensing is in the end actually helping us detect this. You will never get magnification of 1,000,000, but you can get magnification of 1,000 much more frequently and with many caustic crossings instead of just once when the star crosses by the overall caustic of the cluster.
And the stars in this model are distributed according to some profile, or is there some data to constrain the distribution of stars as well?
Well, yeah, that's a very interesting question, because of course, if we see this microlensing, this is now a probe to any stars or point mass objects that are there, right? So they just put a model, and of course there's many unknowns. So what is the surface density in stars? What is their mass distribution? You just put a uniform distribution of stars, you set them randomly and according to some mass distribution, and then you just see here that a typical microlensing simulation can more or less reproduce the typical thing you see. As I say, the agreement here of the peak, right, with what was observed is just because this simulation was set up so that you put the mass here, mass there, and try to match the peaks, but there's no reason to really have to match this. It's only the statistical agreement that would make sense to check, okay? This is just for illustration that they did it in this paper.
Okay, thanks.
Okay, so now let me talk about this microlensing, and this is with in this paper that we wrote with Teja and Liang. So imagine now that this is, we have the critical line of the cluster. It's this red line, and I'm looking at the critical line on a very small part of it, and I'm going there. I zoom up on it and I look at a very, very small structure. So on this very, very small scale, you know, the cluster lensing caustic looks like a straight line because this is like a very small piece of a giant critical line, okay? And then I look what happens if I put the star close to it. So first I put the star here, right? And then the star will develop this critical line corresponding to the caustic in the source plane like this, because, you know, there is the effect of the shear of the cluster. And this critical line is basically much bigger than it would be if there was only the star there. Is that the surface density of the cluster is already causing lensing and magnification to almost reach critical surface density. So that means you're already very close to being able to get multi-Gs, right, and reach the critical value of the surface density that would allow you to get this very high magnification. The star only needs to add a tiny little bit to the cluster, and then you already get multiple imaging. And that means that the critical line around the star gets really magnified and boosted, much bigger than it would be with the star alone. In fact, as the star gets closer to the critical line of the cluster, this kind of infinite figure of the critical line gets bigger and bigger until it merges. And now you see with the star here, and this is what the critical line would be. The cluster one and the star one have merged, right? And then the star can get, this is also how the critical line of the cluster gets modified because of the presence of the star in these positions, okay? And then when the star goes to the other side, then the infinite figure switches, now oriented the other way, right? And now also if the star is sufficiently close, these critical lines merge. Okay, now this happens with one star, but then if you have many stars, then this is what you get, right? The stars that are far away from the critical line get all these infinite shapes, here in one orientation, here in the other, but then the ones that are close, they not only they interact with the cluster caustic, but they interact among themselves, and they produce a more complicated network. So this is basically the corrugation of this cluster caustic into these microcaustics. On a large scale, you'd still would look like, you know, you have the caustic of the cluster, okay? But when you look at this on a very, very small scale, you start to see that there's really this very interesting and intricate structure to the caustic, which we call corrugation. And so these lens incrustations are magnified, and then what happens is that as you increase the number of stars that you have in the cluster near this critical line, there is a critical value of the surface density of stars, which we call kappa C. This is the critical value of the convergence, which you can show goes with the Einstein radius of the star when it's acting alone, times this gradient. This D is the gradient of the eigenvalue of the cluster that is zero at the critical line. So it's proportional to this. And when you calculate this critical surface density, so the critical surface density means if you're above this kappa C, you start being in the regime where the stars near the critical line are all interacting with each other. They cause this, they produce this network of microcaustics. And if you're below kappa C, then you have so few stars where you would have, you know, just one here, another one there, right, with their infinite signs. But then the cluster microcaustic would just get very slight perturbations, but it would still be here basically with only slight turns like that, okay? Okay, so this kappa C, when you calculate what this critical surface density is, it's a very small number, 10 to the minus 5, okay? And that means you really need to add very, very few stars to just get into this picture of a very complex microcaustic, well, corrugation of microcaustics. This depends, of course, on the Einstein radius of the stars and on this value of D, the gradient of the eigenvalue, okay? But so this is very small. And when you put the numbers here, typical for stars, micro arc second for the Einstein radius, and an inverse of 12 arc seconds for the characteristic gradient of a typical cluster of galaxies in angular units, well, that's this very small number that you get. Okay, so that means that, you know, what is going to be the surface density in stars? Well, typically it's going to be maybe 1%, I don't know. So baryons are perhaps 10, 20% of the mass in clusters. Stars are maybe less than that, you know, 3% if most of the baryons are in hot gas, but then the stars in galaxies are maybe 3% of the total mass. And if 1/3 of these stars are not in clusters, not in galaxies, but are in the intracluster medium because they got stripped from galaxies, right? Pulled away in tidal arms of all kinds, and then the stars are just out there in the middle of the intracluster medium orbiting around. Well, you've got these stars and maybe there'll be 1% of the surface density, or maybe even less, 0.5%. But that's more than sufficient to break this caustic of the cluster into these little microcaustics and make a mass of microcaustics and this tremendous corrugation. Here, what I show you is a simulation of this thing. So we expect microlenses, at least from intracluster light. The region of corrugated microcritical lines will get bigger and bigger as you get more and more microlenses. In fact, it has a width in the image plane proportional to the convergence of microlenses or the surface density of microlenses, okay? And so because we are typically so much above this kappa C, this critical surface density, in fact, what we'll get is a very, very complicated network. What I'm showing here is a simulation of this corrugated critical line. This band here is the band of corrugated microcaustics. Okay, and in this simulation, in this particular plot, you really can't see anything because it's so small. You know, you don't have a resolution to see all the mass of microcaustics you have here. Okay, so then in this simulation, we have a surface density of stars that's only about 17 times that critical value, kappa C, I was telling you before. In a real cluster, we estimate that actually the surface density of critical lenses will be maybe 300 times the critical value. It just becomes impossible to simulate. There's so many point masses that it just takes too much computer time. So we did this case of about a factor 17. And then, imagine this region here of the image plane that was simulated. We zoom up on it, we have this. Okay, now you can already see here a little bit the microcaustics. You can start seeing them. Now let's zoom up this piece here also, and you have this. So you can see the structure that you've got, right? Every point here is a star. This was the original cluster caustic, and this is what you get, okay? These many, many microcaustics, and then you get this whole thing. And then when you go outside this region, you start getting the isolated infinite signs here and there, okay? Okay, and then you can figure out some properties of, what's the width of this network of microcaustics, how it behaves. It's proportional to kappa star squared, okay? And what's the maximum magnification you will get, and so on. So there's very nice, you can analytically get various properties of this. So then when you try to simulate what you should see, then first of all, you can find what will be the maximum typical peak magnification you will get. Well, it's much reduced from the case of without any microlensing. It turns out to go as this kappa star to the -3/4, the surface density of the stars. Okay, and this is a simulation of the typical thing you will get as you approach the cluster caustic, which should be here. Okay, but then because of the microlensing, instead of just seeing this smooth light curve as you approach the cluster caustic, where you get the magnification up to here, then what you see is you see these many events as you cross the many microcaustics. Okay, and then basically you get a very high density of microcaustics at the end on a rather narrow region here, but you can get high magnification over a much longer width. Okay. Where here the density of microcaustics is less, but the magnification is higher, is as high as here, okay, and this is what goes as kappa star to the 1/2, and this region of high density is what goes as kappa star squared. Okay, these details I don't need to go over them very much because it's a bit complicated, but basically now if we take the star I was talking about before, 50,000 solar luminosity star redshift 1, I can have magnification of 10,000, then it will be magnitude 28 for 100 years. But now microlensing will cause all these peaks. So in these 100 years, I will get various peaks when I will be able to see the star. Okay, so what we would predict is that if we've seen one of these events, then there will be repeated events in the same place kind of randomly because of this microlensing going on. Maybe from the same star, but maybe there's also other source stars. Okay. So now, of course, when we see these peaks, what this is probing for us is the presence of these microlenses, and these we think are intercluster stars. So now we can explore things like their density, their mass distribution, their mass function. So that becomes very interesting. And also because in addition to stars, who knows, maybe there are other things. At least there should be, for example, these black holes that LIGO is detecting with gravitational waves, right? We have an old stellar population in the cluster, so there should be black holes of various masses. These will contribute to the microlensing. In fact, they'll be the most massive objects producing microlensing, even though they're quite rare, so maybe they're difficult to detect. We have to study a lot of these light curves before being able to measure any such thing. So I would like to, more generally, this can be helpful in answering this fundamental question: what is the dark matter? And in particular, if the dark matter causes any kind of small structure in the distribution of dark matter, here is where we are able to perhaps see something, okay? So is there small scale granularity in the dark matter distribution? For that, we have to go to this kind of observation, okay? So probes of the small scale clumpiness of the dark matter, we don't have many, but we have a few. We also have these microlensing limits in the Milky Way. Of course, you know about the microlensing searches that were done by Macho and Abell. These put limits on any compact objects in the dark matter that are really compact. There's also gravitational lensing effects of subhalos in galaxies. For example, people have looked at the flux ratios of multiple images of quasars. Okay, so lensing provides several of these things. There's also tidal streams that people are exploring today, and people are saying, you know, if there are subhalos of dark matter in the Milky Way, then they'll impact on these tidal streams. So there's a few ways we can check for the small scale structure in the dark matter, but not a lot. But this basically opens a new possibility. Yeah, and there's many possibilities for dark matter granularity. So one theory is that dark matter may be primordial black holes. It could all be compact objects. Even the standard cold dark matter model, you know, you predict subhalos that are dark, not visible through stars. Then you have to see them through lensing, or maybe these effects on tidal streams. There's ultralight axions. If dark matter is ultralight axions, then it would behave like a classical scalar wave, and we would see waves of dark matter going through a halo. So things are kind of trembling. And then there's also kind of axions that are in the QCD axions, and then it turns out these can produce mini halos. So I would just now focus in the rest of the talk. Okay, I don't have much time, but so let me just talk a little bit about QCD axions. And QCD axions, as many of you know, they were proposed in the 1970s, and they are really a wonderful thing. In fact, I think they are now the best candidate for dark matter, because first of all, in particle physics, they solve this long-standing particle physics problem, the charge parity, strong charge parity problem, which in this problem, basically, you do not understand why you don't have a term that violates charge parity conjugation, and among other things would produce, for example, an electric dipole moment for the neutron. And we don't observe this electric dipole moment, and we don't know why. And it is smaller than what you would typically expect by a factor 10 to the 10. So that is a problem. And Petchy-Quinn proposed this mechanism for solving this problem, which is to assume that there is an axion field, and then this term is eliminated because you just go to a minimum of the potential, and then this basically generates the axion field. The nice thing is that this axion field could be produced non-thermally and create the dark matter in the early universe. So here you have a case where we have a prediction in physics that is just motivated by a problem in particle physics, but then it also predicts that you can produce dark matter. And so we connect the two things here. So if this axion exists, then it would produce isocurvature fluctuations, at least in what's called a post-inflation scenario. And then this axion density these isocurvature fluctuations would start collapsing roughly at the time where you reach matter radiation equalization. So this is redshift 3500, quite high redshift. The normal adiabatic fluctuations in cold dark matter collapse much later, at the time of galaxy formation. But if you had such a thing, then these isocurvature fluctuations would be on a very, very small scales, basically at the time of the QCD phase transition, the time of the horizon at that time. And so then initially those would be, even though they are fluctuations of order unit in the axion field, then of course at very early epochs, the radiation dominates, so this would not collapse immediately. But then as soon as the matter dominates, then these things would collapse. And they would produce axion mini halos. So you'd actually have formation of structure from isocurvature fluctuations at much smaller scales than we know from galaxies. They would produce these mini halos, and the typical mass you expect is the mass of an asteroid, like 10 to the minus 12 solar masses, and the typical size is maybe 0.1 AU. Some uncertainties on this, but these are just typical numbers. And this was described in these papers by Hogan and Rees and Kolb and Katchev. This in the middle of the 90s, they did some rather detailed distribution calculations already. So this is a very interesting prediction. There would be these axion mini halos. They are very difficult to detect. So it could be that the dark matter is not smooth. You know, it's kind of granular and has these kind of clumps and very, very small scales. But then how do you detect them? In fact, there would be axion minihalos created at a typical scale, but then because they would be produced randomly in space, they would have a white noise power spectrum on larger scales. They would interact and merge in the usual hierarchical clustering process, just like it happens with galaxies, but with this white noise power spectrum, where you get the radius of the halo proportional to mass to the 5-6. As you go to larger and larger scales, you get merges and merges and so on. These merges would collapse later, from these random noise fluctuations on larger scales. So can we detect such mini-halos by gravitational lensing? You would hope gravitational lensing is one way to detect them. Gravitational lensing is sensitive to all the mass. Can we go to these very small scales? Well, when you try to estimate this, you have one main problem to detect these things. You cannot detect them like in the usual microlensing experiments, okay, where they can also, maybe you could go down with very short events to these very low mass scales, because their radii are too big, so they're too extended. So if you calculate what is the surface density of such a halo, such a mini halo, it's very small. And the convergence that it produces is only about 10 to minus 4, 10 to minus 3. That's 10 to minus 4 times what you need to produce multiple images, okay? So the magnification that you would get if such a mini halo passes by the line of sight of some star is only at the level of 1 part in 10 to the 4. This is extremely difficult to detect, okay? And it will be also a rather short event. So that's basically the problem. Lensing effects are very weak. And when you go to these larger halos produced by the white noise fluctuations, it gets even worse, kappa going as n to the minus 2/3. So how to detect them with such small kappa? Well, one way is, I have put here some description of a science fiction thought experiment. Okay, imagine that here I have this axion mini halo floating around in space. There's millions and billions of these in the galaxy floating around. And these are the dark matter. And then let's say we have a spacecraft and it flies by interstellar space. It goes by one of these things and we find, look, we've been deflected by something. There was a mass deflecting our trajectory, but I'm sending some radar there to see if I have an asteroid, and there's nothing, okay? Well, if you have several of these, you can tell, you can try to guess the trajectory, the mass of this object. When you have several deflections measured, eventually you figure out what's this thing. Then you send another spacecraft to catch up with it in the middle of space. It meets the mini halo. It goes to a rendezvous, right? Not just flyby, to a rendezvous with a very, very tiny relative velocity so that it can get caught in orbit around the mini halo. And now you can do your wonderful experiments with lasers and so on, and measuring the density profile of the dark matter just from the orbit of this spacecraft going through this. So it'll be, very interesting. You orbit around something, you can't see anything there, right? It's just axions. Maybe then you can put your experiment with the Primakov effect, right? You have an axion detector here with magnetic field and see if there is indeed a very high concentration of axions here. Okay, well, that's basically, it'll take a long time for us to be able to do this. Once we can do it, it'll be very nice. But in the meantime, because this is very, very difficult, right? Almost impossible to detect these axion mini halos. In the meantime, we can think about how about lensing. Even with this very low kappa, can we detect it?
So
yes.
What will be the probability of such a axion mini halo crossing the solar system?
Yes, you can calculate that easily, but basically at the characteristic time, if you ask when will be the nearest one to us, right, at a random time like now, for this mass of 10 to minus 12 solar masses, it's about maybe 300 astronomical units away. And they're, of course, flying by at 300 kilometers per second, all right? So, and they're just randomly passing by. Yeah, but so, and of course, if they get too close to the sun, they get tidally disrupted. So they would produce streams and so on. Typically, only a fraction of the dark matter would be in these mini halos. Others would be already.
There were a few objects which had some anomalous acceleration that we had detected.
Excuse me?
There were a few objects in the solar system where we detected this anomalous acceleration.
Yes, yes, but this is not at all.
To explain that using these things?
Yeah, but this is not at all this is a much bigger effects than anything that would be produced by these mini halos, and you know, it's a kind of different thing. Yeah. Okay, so well, let me go directly to this plot to show you basically the main idea. So the main idea is when you have one of these highly magnified stars, and it's going through this corrugated network of microcaustics, then here is where the lensing that you observe and the magnification you observe is sensitive to tiny variations of that kappa, right? That surface density of the dark matter. If you have very tiny variations, then you're going to get changes in your microcaustics. And then the idea is that in addition to the microlensing by stars, there would also be this microlensing by axion mini halos. And here is where, you know, when you have two images of a star around a microcaustic now, then there would be essentially the presence of axion mini halos would produce this, and they would produce another level, second level of microcaustics within microcaustics, so at an even smaller scale, and a lot of irregularities in the magnification you would get. So whenever a star goes through a microcaustic, and then if you measure the light curve in detail, remember the light curve I showed you earlier, we can predict it, and we can put models of limb darkening and so on, but then the axion mini halos would be producing this kind of variations. Okay, and why is this? Because now even a kappa fluctuation of 10 to the minus 4 becomes very important when you get close to the caustic, where, you know, 1 minus kappa minus lambda, your eigenvalue is just so close to 0. So if you put a little bit variation of 1 in 10 to the 4, then it determines whether you're exactly at 0 or a little bit away from it. So then you could get these perturbations. So if you see these small scale, short time scale perturbations around the expected light curve of a source star crossing the microcaustic of one of the stars in the cluster lensing, then this would be indicative of a, you know, a deeper level of substructure in the dark matter. Okay, and of course this is also difficult today because, you know, we have to observe many of these highly magnified stars, and we would have to do good photometry on it and do the statistics and these variations in the light curve. So this is something that would require a powerful technique, but maybe James Webb Space Telescope and maybe also these giant ground-based telescopes that are being prepared now, 30-meter, 40-meter telescopes, they will be able to see this, and with adaptive optics, you know, maybe you can discover many of these. These highly magnified stars are such that we have now seen just the tip of the iceberg, but if you go a little bit fainter, then the number that you will discover will grow very rapidly as you can go fainter. So this is basically opportunity we have here for checking if dark matter is made of axions and there are these structures. Finally, okay, I'm a little bit over time.
Sorry to interrupt you, Jordi, but how would you distinguish in that scenario the effect of stars in the lensing cluster from such mini halos, from these perturbations in the light curve?
Yes, these axion mini halos would produce perturbations on a shorter time scale and of a different statistical nature. So essentially, without the axion mini halos, and if the dark matter is smooth, then you would just see the crossing of the caustics due to stars. And then when you get close to a microcaustic, it's dominated by two images near this microcaustic, and it follows the light curve that you can compute. The presence of the axion mini halos means that you have structure everywhere on a shorter time scales, right?
I see. Okay, thanks.
Yeah, I mean, of course, it is also possible that you have lower mass microlenses, but like, I don't know, brown dwarfs or planets, but I think the number of those will not be so much, right? And I think the statistical properties will be quite different. Okay, so just mention also one last thing, that even standard cold dark matter predicts the presence of these subhalos, and that you can also use this microlensing to test the presence of subhalos. So here is again, you know, this is a simulation that we did where if you had no subhalos, this would be a smooth critical line going like this. and then you imagine that you have stars or whatever you're seeing lensed in the galaxy. So you have one image, the blue one, the other image, the red one. You calculate the middle points, and then you get these pink crosses. So then the middle points should indicate you the position of the caustic, position of the critical line in the image plane, just between the two images, these pairs of highly magnified images. And here you have another one. The middle point is here, here, the middle point, middle point. If you had a smooth caustic, these middle points would all follow a straight line on a small scale, following the caustic, the critical line, I mean. But when you have subhalos, it causes all these irregularities, and then you see these deviations, which would indicate the presence of subhalos. Now we're going to scales of, here is subhalos of 10 to the 8 to 10 to the 9 solar masses. Here is 10 to the 6 to 10 to the 9 solar masses. The 10 to the 6 ones add additional small scale structure. Okay, so this is basically just standard CDM testing the presence of subhalos. So that's another application you could get from this kind of highly magnified images. Let me just conclude from what I've described to you. So we have these individual stars at high redshift, can be very highly magnified, that we can detect with our most sensitive telescopes. Already we have at least 2 stars that have been detected highly magnified, and we expect there to be more. And in fact, the HST archive has been examined because there may be some images of these highly magnified stars that are in the archive but not yet discovered. So some people are going through these and trying to find more cases. In general, you only need this tiny surface density of point masses in a cluster to break away from this idealized model of a smooth critical line, and then you get instead this corrugated network of microcaustics. So whenever you have one of these highly magnified images of a star, you expect to see lots of random variations due to microlensing, just if you have the expected stars, intracluster stars floating around in the cluster. So these photometric variations and the distribution around the critical lines of the highly magnified star images are a powerful probe to this granularity. One thing that I went over rather quickly is that one of the best probes to these microlenses is that the thickness of the corrugated network of microlenses, where you see the highest magnifications, it has a thickness around the critical line, which is proportional to the surface density of these lenses. So just if you can just measure the thickness where these images appear, you get the surface density of the microlenses. And then as we observe fainter point sources, the number of detectable lensed stars should rapidly rise. This is what we expect, because there's many more fainter stars compared to the most luminous stars, so there will be many more of them. So this is promising to constrain many things in the granularity of the dark matter, such as QCD axion minihalos that I told about. That's very exciting, but also primordial black holes in the dark matter, if they are there, of many masses. You can probe down to primordial black holes of very low masses. And also ultralight axion waves is another one. So I will stop here. Thank you very much. We can go to questions.
Thank you, Jordi. So I think we have time for questions. We already have a few questions, but anyone have any questions, you can raise hand.
Jordi, what number should one keep in mind for the redshift range for observing such stars with HST, JWST, and 30-meter telescopes?
Yes, the redshift range will be the typical one of lenses. So most of the galaxies that are observed to be lensed by clusters are typically at redshift 1, and there are a few that can go up to redshift 3, 4. Okay, actually for this, it is advantageous to take the lowest redshift cases. So for example, the first arc that was discovered at redshift 0.72, that's best because simply because the stars are closer to us, so they're a little bit brighter. And then here the limit is always how faint you can go.
I see. Maybe just a quick question, Rishi, if I can ask. So Jordi, in one of your slides, you also had when you were discussing this axion minihalos, you had a plot showing some power spectrum. Was that the matter power spectrum for?
Yes, I went over this thing rather quickly, but basically it is this plot. So here the red line is the usual cold dark matter power spectrum that is responsible for forming galaxies, instead of just showing power spectrum here as a function of wave number k, here in megaparsec to the -1, what I've shown is power spectrum times k cube. And so that basically tells you what is the amplitude of linear density fluctuations. So that amplitude keeps growing as you go to smaller and smaller scales here. Right, and then so it has this characteristic shape of the cold dark matter power spectrum. This grows only logarithmically at very small scales, and then when you go to large scales, it goes as k to the 4th in the limit of very large scales. And this is the place where it turns over basically from the crossing of the horizon at the time of equalization. Now, if you had these axion minihalos, what would happen is that as you go to much smaller scales than what can form galaxies, basically, at some point the power spectrum would boost up. Okay, but now this is not due to the adiabatic fluctuations that supposedly were formed during inflation, but now they are isocurvature fluctuations, and they're isocurvature where, you know, what changes is the dark matter density compared to both photons and baryons, right? The photon to baryon ratio still remains fixed. So these isocurvature fluctuations are rather more difficult to limit, and they would be responsible for this growth of power on very small scales that would form the minihalos.
Okay.
And these are just different models because this parameter of the initial mass of the mini halo is rather uncertain. This is a not parameter.
Okay, any other questions?
So maybe just a quick one. Again, for several of these things, it appears that confusion will be a significant challenge, right? For example, even on the plot that's on the screen right now for the light curve, you will have multiple stars getting magnified, showing different levels of fluctuations at the same time.
Yes, yes, I agree. This is still, of course, you know, a rather difficult observation to do for the future. So we can start discovering some of these super magnified stars now. But then, of course, you have to study the statistics. And first, you can study the mass function of the intercluster stars, and then try to figure out if there is any anomaly once you measure the light curves with more detail.
Okay, I guess there are no more questions. So let's thank Jordi, and I will stop the recording now.
Okay, thank you very much. It was a pleasure.
Thanks, Jordi. Thank you very much.